going to be that bad, right? I mean, I could throw names at you and it'll sound fancy, like hypergeometric distribution, but it's like, I could throw like a normal quantile plot. I can throw that name at you too, and that'll sound intimidating also. It's just because you don't know what the words mean, right? But once we build up to those concepts, they're not going to be as challenging as long as you're with me every step of the way. All right. We're all sufficiently terrified now. All right. Yeah, that wasn't the point of all that. It's more so that you can kind of like not miss the transition between when it's easy and when it's not easy, because there's like that brick wall where probability gets hard, and if you don't have sufficient speed to blast through that brick wall, then we can have a problem. But hopefully that won't be the case. All right, a PDF. Unfortunately, in math, we kind of take liberties with abbreviations and then abbreviate in ways that would be completely confusing to a person who works with that term in real life. It stands for probability density function, right? So that's just what it is, but PDF is really just saying a function, a normal curve is an example of a PDF. It's a function that contains information related to probabilities. All right, so what we have here is a skewed distribution, but we could have a normal distribution. You could have a bimodal distribution, which means that you have two humps. All right, you could have multimodal, so it could have like 30 humps, hills and valleys all over the place. But the bottom line is the total area has to be equal to 1, and the justification for that is if it's going to model a probability situation, it's got to contain 100% of the values. All right, and every point on the curve has a vertical height greater than or equal to 0, because every point on the curve represents a probability. All right. So essentially, what we're going to be doing is taking our knowledge of functions and applying it to a probability context. All right. And it's kind of weird because you might think of probability values as being discrete values, in that you're talking about countable instances. Because discrete data, you're talking about finite values, things that you can count up, like number of chairs in a room, number of people in a building, and stuff like that. Right? But this is a continuous function, right? Continuous in the calculus sense or pre-calculus sense, depending on where you're at. All right? So that's just talking about, the graph having no gaps, jumps, holes, or any other kind of asymptotes, all right, of the vertical variety, right? Horizontal asymptote is fair game. In fact, this one has a horizontal asymptote at 0. So the only time it would ever get to 0 is if it got out to infinity. All right, so we'd be looking at, if I define this as P of X is equal to my PDF, my probability density function. What this is saying is that the limit as x goes out to infinity of P of X would be equal to 0. All right. So the vertical height greater than or equal to 0, it's more of a theoretical equal to 0, right? Because you'd have to get out to an x value of infinity in order for it to actually be on 0. All right. That's how we represent a function, because without involving a piecewise, how could you come up with a single equation that would be a curve and then actually go completely horizontal? All right. In order to do that, there'd have to be a corner. All right. If there's a corner, then you're talking about a point of, now this is only for calculus, but you're talking about a point that's non-differentiable. All right. If it's not differentiable, then the calculus doesn't bear out. All right. So one of the things is that we're talking about area under a curve. That's integral calculus. When you get into integral calculus, that's kind of an issue, because in order for that to be the case, or anything to work, the in terms of the area, it has to be something that's differentiable and anti-differentiable. So this is not something that would be on the test, but if you are somebody who's learned about antiderivatives, you might recognize this symbol. And we'd be talking about the improper integral going from negative infinity to infinity of p of x dx. That would be equal to 1. All right, so that's the justification that the area under the curve would be equal to 1. Now, if you're taking regular calc, you might learn that in college at some point. Right? If you're taking AB calc, you'll learn that at the end of the year. If you're taking BC calc, you may have already learned it. All right? So, like all over the place. But basically, this is like kind of enrichment stuff. And really, it's my way of saying that a lot of the things in probability and statistics, you kind of have to take it on faith as it's a rule that works, because all of this stuff, and in fact, even why does it do that? I don't know. They just changed the bulb too. All of the stuff, all the rules that you learn, even going back to standard deviation, its justification is grounded in second year and third year calculus courses. Right? So you'd actually have to take, and that's how it used to be. You'd have to take all of the calculus classes before you would even think about taking a stat class. Now they kind of changed it so as long as you use the rules and don't question where they came from, you can still evaluate. So it became more of an analysis thing rather than learning the mathematics behind it. All right. So the density curve is always on or above the horizontal axis. I think that's clear based off the diagram and not even the calculus statements, all the parameters that were stated before. The median of a density curve is the equal areas point, right? So if you were to try to determine that equal areas point, you'd have to use integral calculus, but you could also just generally eyeball it, all right? Because, you know, the kind of questions they like to ask on the AP are, like, what's the relationship, given this graph, the graph of a normal curve or a density function of some kind, what's the relationship between the mean and the median? Is the mean bigger? Is the median bigger? You know, that kind of stuff. All right. The mean of a density curve is the balance point. All right. So kind of like a seesaw. If you were to try to, if this were a solid material, obviously this side would be the heavy side, right? So the mean would be where you would put science word. Is it a fulcrum?
Fulcrum, yeah.
Okay, thank you. Yeah, where would you put the fulcrum so that it would be completely balanced? All right, that's how you're going to visually identify the mean. All right, the median, it's again, it's an eyeball thing because you look at it and say, all right, does this area feel like it's about the same amount as that? Yeah, maybe yes, maybe no. All right, so then a good question would be, how can we figure out with a little bit more precision where those balance points are without having to get integral calculus involved? Fortunately, your calculator is programmed to understand integral calculus, right? Except there's not in the way that you might think. Like if you know how to use the integration function on your calculator, that's cool. There's an even better approach that we could use. All right. So that brings us to the page. And by the way, if you were ever wondering what the equation was, the function equation for a normal curve would be, it's that right there. Look at that. That's pretty beefy. I mean, it does have an exponential feel to it. You know, and when you have a composite function, you know, composition of functions, plugging one function inside another, the resulting function always takes on characteristics of the two separate functions. So I'm composing a quadratic function and an exponential function. And when you think about the normal curve, doesn't it have characteristics of a parabola and an exponential function at the same time? It's the merging of the two ideas, right? So this formula structurally should make sense, but it may be, you know, like, well, I'd never come up with that. But, you know, like when you really dive into it, it should make a great deal of sense, all right? And then what I did was I put the integral calculus way of finding area under the curve and a little bit more related to that. But what I wanted to do is go back to that empirical rule and show you how that calculator would come up with those values for you. On the next page, there's a table. That table sucks. Okay? That's the old school way of doing it before they programmed your calculators to do all that stuff for you. They will actually give you those tables on the AP exam, but if you even bother looking at them, then the day of the AP, then that's just an indication that you haven't listened to a word I said all year. All right?
But we don't have to memorize those.
You do not. You do not. Well, there's like one that you should probably know, and that would be 0. As the z-score of 0 has 50% on either side of it, but definitely don't need to memorize. And also after this, you'll see that you don't even have to memorize the empirical rule because the calculator is going to give that to you also. All right. So in the last few minutes that we have, I'll just walk you through the process. Very straightforward. We're going to be kind of living in a new menu for a little while, and that's the distribution menu, second vars. And so you have a lot of different options here. So second vars brings you to the distribution menu. This is a very important menu because throughout this unit we're going to be dealing with normal distributions, geometric distributions. All right, so if you think of geometric sequences and series, there's a distribution for that. All right, right now we're looking at a normal distribution. All right, normal CDF, the C stands for cumulative. All right, the P, the normal PDF is probability density function. That gives us the height at any particular value, but what I want is the area over an interval. So what I want is option 2, which is normal CDF. It asks you for, well, I'll just show you. The lower bound, the upper bound, the mean, and the standard deviation. All right? So the lower bound, if I'm going from -1 to 1, the lower bound should be -1. By the way, it pre-installs values like -1 E99, +1 E99. That's the calculator's way of saying negative infinity and positive infinity. All right, so if you need it to go out to infinity, you just do 1 E99, that's infinity to the calculator. But I just need to go -1 to 1. The standard normal curve, so -1 to 1. Standard normal curve has a mean of 0 and a standard deviation of 1. If it were any other kind of normal curve, you'd have a different mean and standard deviation particular to the problem. So hit paste and enter, and it'll give you about 0.683, which is a verification of the first part of the empirical rule. So on your own, try that for 95 and 99.7%, and then we'll pick up with that after the break.